Hey everyone, and welcome back. Today, we're jumping into a really cool coding problem. It's all about finding perfect balance in a sea of zeros and ones. It's such a clever puzzle, and the solution, it's a pattern you're going to want to keep in your back pocket for sure. So, picture this. You've got this long string of just zeros and ones. The question is, can you find the longest possible chunk inside that string that has the exact same number of zeros and ones? It seems simple on the surface, right? But how would you even begin to tackle that? All right, let's get a little more technical, just like you'd see it on a site like LeetCode. We're given a binary array. Our job is to find the maximum length of a contiguous subarray that has an equal number of zeros and ones. And those two words are super important. Contiguous, which means it has to be an unbroken sequence, and of course, equal. To make sure we're all on the same page, let's look at a super simple example. The array 0, 1, 0. Well, the subarray 0, 1 works, one of each. Its length is 2. Same with 1, 0. But the whole thing, 0, 1, 0, is unbalanced. So the longest balanced subarray we can find has a length of 2. Easy enough, right? Okay, but that was a tiny array. Imagine trying to do that with thousands of elements. It gets messy. That's where this next idea comes in. We're about to look at this problem from a completely different angle, all thanks to one simple but honestly genius little trick. So here it is. This is the big aha moment. On the left, we're thinking about counting two separate things, zeros and ones. It's clunky. But look at the right. What if we just decide to treat every single zero as a -1? All of a sudden, this isn't a counting problem anymore. It's a sum problem. And this is why it's so powerful. Think about it. If you have an equal number of ones and -1s, what happens when you add them all up? They perfectly cancel each other out, and the sum is 0. We've just turned this tricky balancing act into a much simpler goal. Find the longest subarray that adds up to 0. Okay, so our new mission is clear. Find the longest piece of the array that sums to 0. But how do we do that without checking every single possible subarray? That'd take forever. We need a couple of key tools to do this efficiently. Tool number 1 is the prefix sum. It's exactly what it sounds like. As we walk through the array, we keep a running total. So at any spot, we know the sum of all the numbers from the very beginning up to that point. This little trick is incredibly handy, as you're about to see. Now stick with me here. Imagine we're calculating our prefix sum. We're walking along, and at, say, index I, our running total is 5. We keep going, we add some numbers, we subtract some, and then later, down at index J, our running total is 5 again. What does that tell us? It means everything in between those 2 points, all those numbers between index I and index J, must have added up to exactly 0. If our total didn't change from point A to point B, then everything in that segment had to have canceled out. And bam! That's our balanced array. Okay, so this is the next logical hurdle. It's great that we can find these pairs, but we can't be looking back through the whole array every single time we calculate a new sum. That would be way too slow. We need some kind of instant memory. And that's our second tool, the hash table. You might know it as a map or a dictionary. It's perfect for this. We'll use it as our memory bank. The key will be the prefix sum we've calculated, and the value will be the very first index where we saw that sum. This lets us check if we've seen a sum before, instantly. All right, let's put it all together into a game plan. Step 1, we start our running sum at 0, and we put a special value into our hash table. We say we saw the sum 0 at index -1. This is a little trick to handle cases where a balanced array starts right at the beginning. Then, we just loop through the array. For each number, we update our sum. Then, we ask our hash table, hey, have you seen this sum before? If the answer is yes, we calculate the distance from our current spot to the spot we stored earlier, and we see if it's a new record for the longest length. If the answer is no, we just add this new sum and its index to our memory. And that's it. That's the whole algorithm. So the theory sounds good, but let's actually watch it work. We're going to take an example and walk through it step by step to see how the sum and the hash table work together to find the answer. All right, let's trace this out. We start with our hash table having 0, -1. Okay, index 0, our value is -1. The running sum becomes -1. We've never seen that before, so we add it to our hash table. -1 is at index 0. Next, index 1, value is 1. Our sum goes from -1 back to 0. Have we seen 0 before? Yes, we stored it at index -1. So the length is our current index, 1, minus that stored index, -1. That's a length of 2. Our max length is now 2. Okay, Now let's jump to index 3. The value is 1, so our sum becomes 0 again. Have we seen 0? Yup, still at index -1. The length is our current index, 3, minus -1, which is 4. That's our new max length. Finally, at the very end, index 5, our sum hit 0 one more time. The length is our current index, 5, minus the stored index for 0, which is still -1, and that gives us a final length of 6. And there you have it. 6 is our final answer. The algorithm found that, in this case, the entire array was the longest balanced subarray. Pretty cool, right?
So what's the big deal here? Well, it's not just about solving this one problem. It's about recognizing this incredibly powerful pattern. Once you understand these building blocks, you can use them to solve a whole class of other problems.
So let's recap the toolkit we just built. First, we transformed the problem to make it simpler. That was the -1 trick. Second, we used prefix sums to keep track of a running state. And third, we used a hash table for instant memory of past states. You put these 3 things together and you get this beautiful, elegant solution that only needs to look at each element one time. That's what we call O of n time complexity. It's super fast. And that's really the question I want to leave you with. This pattern, prefix sum plus hash table, is a real game changer. Now that you've seen how it works, start thinking about where else you could use it. Anytime you see a problem about finding a subarray with a certain property or some kind of balancing act, this pattern should definitely pop into your head. Thanks for diving into this one with me.